Hi, in this video we talk about elasticity in momentum. Notice that this is not the official syllabus in IGCSE physics, but then understanding this can help you to understand the whole idea of momentum better. So first of all, we have to understand that whenever we have collision, assuming there's no external force, then momentum will always be conserved. So no matter it is elastic collision, or the so-called partially inelastic or perfectly inelastic collision, no matter what happens, momentum still conserved. However, the difference is that simply whether or not the Ke will get to be conserved or not. So only in elastic collision, then the Ke will conserve. So that means the Ke before collision and after collision will be the same. While for inelastic, they will not. Obviously, it will be less because maybe there are thermal energy or sound energy that got transferred from Ke. And in the extreme situation, we call it perfectly inelastic. This is when the energy loss is the largest. And in this case, we'll find that the objects always stick together. Okay, so here is a simulation from PhD. I'll put the link in the description below. You can try it out and play around with it. But let me just show you the simplest cases, okay? And that is the elastic collision, right? Which we talk about, partially inelastic and perfectly inelastic. So we'll start with elastic first. So we have to set elasticity to be 100%, okay? So perfectly elastic. And I'll have to make more data to be visible, so then it's easy for you to see. Obviously, I have to take kinetic energy, so you can see 0.44, which is the total Kd. You can try to calculate by half mv squared on object 1, object 2, and just add them together. It's going to be 0.44. I double check it. So if you want, you can pause the video and check it yourself. As for momentum, you can see that object 1, 0.5, object 2, negative 0.75, which simply calculated by mass times velocity. Okay, so you can see the total is negative 0.25. Okay, negative. So remember that this is the momentum before the collision, and we are going to check whether or not the momentum after is still 0.25 negative, and Ke is still the same. So let's go. Okay, you can see Ke is the same, 0.44, and momentum, if you try to calculate, if you can't really see it, you can still add them up. Negative 0.63 plus 0.38 is still the same. Okay, negative 0.25. And so for now, what we're doing is I'll reset this, and I'm going to change the elasticity to 50%, and let's see what happened now. Okay, so you can see kinetic energy reduced quite a lot. Okay, it's not going to be half, all right, but then it reduced at least. And then momentum, again, we can try to calculate. Negative 0.34 plus 0.09 is still 0.25 negative. So momentum still remain unchanged in total, but then the Ke is less in total. So that means some of the kinetic energy has transferred to maybe sound energy. So now let's reset again, and let's go to the worst case, all right, the perfectly inelastic case. And so if we try to start again, remember the Ke is 0.44 at the beginning, and momentum in total is negative 0.25. Okay, so you can see that kinetic energy is going to be 0.02 joule, is even less than just now. But then for momentum, if you try to add these two together, I guess you can tell. Yeah, if you just add them together, you know it's 0.25 negative. So that is exactly the same as what I put down here as the table. And so one question that you may ask me is that what actually determined the collision is elastic or not? And the answer is complicated. It depends on a lot of different factors. It could be the materials, it could be how the objects are going to be collide, in what angle, for example. And so you can see just now in the simulation, even for the same object, like it's nothing to do with the mass of the size, they could still have different elasticity. So it's independent of the mass. It's more about some other factors. But then for now, I think we will just have to understand that how the elasticity is defined by how much Ke is being conserved, simply. So here is a question for you to try out, and please pause the video and try it yourself.
A few moments later.
Okay, so the question set here, we've got the mass m, and then the initial height, and it's dropped from rest, so u is 0, and it rebounds back to 2 meters. So if you want, you can draw the diagram that it got dropped from 5 meter, and then when it bounces back up, it's going to be 2 meter only. Okay, and they tell you the time of impact, so this is going to be delta t. Okay, taking downward as positive. Part A asks you what is the velocity before and after the impact. So for before, we will have to think about using different equations. So you can apply the idea of energy you learned in the previous chapter. That is going to be mgh equals to half mv squared, because you release it at rest, and then you before it collides to the ground, all GPE convert to KE. So yeah, this is the equation that you can use. So m will cancel out, and then g will be 10, h will be 5, and then v squared is the one that we want to find, and eventually we can find out v, and that is 10 meter per second. And then for the speed or the velocity after the impact, we cannot use conservation of momentum unless for some reason you can get to know how this ball is affecting the earth. Because if you try to think about it, it's really, I mean, I try to draw in scale, but it's impossible. Like imagine this is the earth, alright, and this basketball or like whatever ball, alright, it's literally dropping on earth, and in fact the ball will kind of move the earth by a very tiny bit. Alright, if you consider that, then you can use conservation momentum. If you don't consider the earth, then the earth is kind of outside of your system, and that will give you an external force, so you cannot be using changing momentum to calculate. So what you can do instead is, here I will recommend you to think about the fact that the object go back to 2 meter. So again, by using energy, you'll be able to find out the answer. So you just simply do the same thing. Alright, because this time, or you can try to do it the other way around if you want to, although it is literally the same. It's a KE that got converted into GPE to 2 meter later on. So this time, once again, the m will actually cancel out, and this time will be the v squared, or I can actually use u, alright, to make it easier to distinguish. So u was like the one before the impact, v is after the impact, and then 10 times 2, because it go back to 2 meter. So eventually you find out the speed would be 6.32 meter per second. But then the question asks you the velocity, so you have to pay attention to the direction. Using energy, very likely it cannot help you to determine the direction. So you just have to add that the velocity after the impact equals to negative 6.32, because it's going back up, right? And we define going down is positive. Part B, asking you changing momentum. So you can write delta P, mv minus mu, and then m you can have 0.3, v is negative 6.32 minus initial 10. So eventually you have negative 16.32 times 0.3, that become negative 4.896. The unit should be kg meter per second. Part C is asking you the impulsive force, and here basically it means the net force during the collision, right, during the impact. So that is called the impulsive force. So simply what you have to do is, using the equation that we talk about, F, well, you can use F equals to ma actually, and that's the net force, obviously, and that should equal to mv minus mu over delta t. All right, if you remember, this is how we derived it earlier, and the one at the top, mv minus mu, is in fact the delta p that we calculated. So eventually we can simply use the answer we have and then divide by delta t, which from the question, and so you can find out the answer. And so the answer is negative 24.48 Newton. All right, and which makes sense, is it's negative because the force that adding on the ball is going to be upward, so then the ball would change its direction, going back up instead. Part D is probably the part that people most struggle with. There's a difference between the impulsive force that we calculated and the reaction force here. You can understand, if you don't know how to do it, you can try to draw the free body diagram. That means the force diagram on the ball during the impact. So if you haven't tried that out, or if you don't know how to do this, pause the video and try to draw the force diagram now.
A few moments later.
Okay, so let me try to do it. This is a ground, this is a ball, and in fact the ball should be kind of squashed, alright, not being spherical anymore, but that's not the main point. The ball should still have weight because you can't get rid of it, obviously. And then the force that actually gets the ball going back up is the reaction force. Okay, and so that's all basically. So what you can do is that you should find out the net force is going to be R minus W, right? I mean, that's the only two forces. And so the force that we have obtained from part C is actually the net force, as we mentioned. So that is going to be 24.48. In this case, we do R minus W, so we kind of convert it back to positive. Or if you like to, you can do F equal to W minus R, because downward is positive and keeping this as negative. So either way is fine, right? But to just make you easy to understand, I guess this way is probably easier. And so we'll find out R minus W, which is mg, right? Which, if you recall earlier, m is going to be 0.3, g is going to be 10, and so eventually you'll be able to find out R, which is reaction force, to be 24.48 plus 0.3 times 10, which is 27.48. Okay, so this is in Newton and this is in magnitude only. So if you really want to express the in terms of the direction as well, I think it's better if I can say absolute value. Or if you really want to don't make it so complicated, then you can just say like how we did, like how I suggested earlier, that is W minus R. Again, because W is going down and reaction force is going up. Or you can also do this, W plus R. Alright, and you may find, oh wait, shouldn't they be in a different direction? What you can do is you can just ignore the direction, alright, just say they add together. I mean, that's the idea of net force anyway. And so you have negative 24.48, and then the weight being 0.3 times 10 plus R. And so you find out R equals to, like what we mentioned, negative 27.48. In fact, this is probably the best expression that we can write down, and you don't have to worry about positive, negative, or anything. Okay, so eventually you also get the sensible answer, which is R in negative. Lastly, part E asking you whether or not the collision is elastic, and obviously it is inelastic. Alright, and so you have to explain the reason by talking about whether KE is conserved. So you can say that KE before collision, in fact you don't even need to calculate, you can know, because before collision it dropped from 5 meter, right? And after collision it can go back up to 2 meter only. So obviously some KE are gone, and that's why you cannot go back up to the same height. So if you want to calculate, that's fine, you can calculate it, but then I guess I'll just say KE before collision is greater than KE after the collision. Alright, and that's why it is inelastic. Alright, so this would be the reason.
Here comes a new challenger!
Here is a bonus challenge for you. This is a picture that go viral a few years ago on the internet, and people were saying that, hey, they want to know which brand or which company made this car, because you can see it's ridiculous that the bicycle can actually hit the car so hard that the car kind of like collapse or crumble like this. So they were saying that, oh, this car company must be very, very terrible, right? And this car is not safe. So after learning this chapter, I want to know what you think about it. So pause the video and try to put down what you think. Okay, I think the answer is actually pretty obvious. If you remember, there was a question that we did earlier about this question, and you should realize that this is kind of a design of a car which actually protects the driver from car crash or collision. And of course, you can't just state the question, right? You have to recall there's maybe some concept or physics equation that can help you to explain. And the equation will be, once again, F equals to mv minus mu over delta t. Okay, and so the reason why it's designed to be like this, is designed to crumble. The main reason is that, again, it's going to increase the delta t. All right, only when you can crumble, then you can increase the time of impact and eventually lower the force, because when you having a car crash, you can't change the final speed because it's going to be zero anyway. And for you, probably you can't change it. I mean, you can change it, but then you can't change it suddenly in a car crash. And so we try to get as high as possible, of course. I mean, the tolerance as high as possible. As for the mass, of course, you can't change it during the impact as well. So that is why the only thing that we can do probably is delta t when we design a car. Of course, the other way you can think about when you drive the car is, of course, you want to make the U lower as well, right? That means when you're driving it, you drive slowly. That's why there are speed limit, obviously. Okay, so that means the argument the people are making on the internet is actually wrong, right? I don't know which brand it is, but no matter what, this car is actually having a very reasonable design.